Greetings. Welcome to the unit on program outcomes PO1 and PO2. In the last unit, we understood the nature and importance of outcomes of engineering programs, where we said there are three levels: program educational objectives, program outcomes, and program specific outcomes at one level, and at the third level, you have course outcomes. Now, in this unit, we'll look at the first two program outcomes, namely PO1 and PO2. What is the nature and importance, and how do we even address attainment of these PO1 and PO2? As we mentioned in the previous unit, program outcomes are what graduates of any engineering program should demonstrate at the time of graduation. They are identified by the National Board of Accreditation. Three POs include addressing and solving complex problems. Two POs mention complex engineering activities. Now, we need to understand what do we mean by complex engineering problems and what do we mean by complex engineering activities, and to decide what to do about them and also whether we are actually doing it or not. Okay. Again, these complex engineering problems are characterized by Washington Accord uh, through what we call to identify what are the characteristics of these complex problems. They called it as WP. You can say the word P possibly refers to problems and W refers to Washington Accord. So, WP1, it is just characterizing what a complex engineering problem is. Cannot be resolved without in-depth engineering knowledge at the level of one or more of WK3, WK4, K5 and WK6 or WK8. You can have a list of that, and if at least one or more of these WKs will have to be are involved. If they are not involved, then it is not a complex engineering problem. So, cannot be resolved without an in-depth engineering knowledge at the level of one or more of these WKs, which allows a fundamentals based first principles analytical approach. Involve wide ranging and or conflicting technical, non-technical issues such as ethical, sustainability, legal, political, economic, societal, and consideration of future requirements. Complex engineering problem is always there are conflicting technical and non-technical issues. Like if you want to build a bridge or if you want to lay a road will have to go through some area that may be where agriculture is taking place, or it may go through a village, then you are displacing them and so on. There will always be lot of conflicting issues which have to be resolved satisfactorily, and it is a complex problem. WP3 have no obvious solution and require abstract thinking, creativity and originality in analysis to formulate suitable models. It is not like just identifying some appropriate formula and substituting numbers in that. So, it does not have obvious solution. You have to make a lot of other related assumptions, and you have to formulate in an abstract way for you to actually come with the solution. WP4 involve infrequently encountered issues or novel problems. You may not be able to come across in some handbook or some standard textbook. You will come across some issues which were not encountered earlier by anybody. So it will become a novel problem, which case you have to find your own solution. Address problems not encompassed by standards and codes of practice for professional engineering. See, some are addressed by standards and codes, but there will be some issues which are not addressed by existing standards, about which you have to come to a conclusion and possibly get even approvals. Involve collaboration across engineering disciplines, other fields, and are diverse groups of stakeholders with widely varying needs. First of all, any large issue will require multiple disciplines. It cannot be simply one electronics or one civil engineering issue. There will be mechanical, electrical, all other issues also likely to come. And there are diverse groups of stakeholders. And each stakeholder will understand or have their own preferences, and you have to operate with that. Address high-level problems with many components or sub-problems that may require a systems approach. You always have something like laying a railway line, or look at that kind of thing when you are trying to have one national highway built through all kinds of terrains. And recently that Chena bridge was built. It took several years for them to understand the terrain, and it's at the highest level that they were able to build. And when you solve that kind of problems, you have it has several sub problems that need to be first solved before you can put it together. It is not as if it is a single problem. Okay. Now, some examples of complex engineering problems. Plan for supplying water for irrigation and drinking to a group of villages in an arid zone. So, in an arid zone, what do? There may be alternatives, but you have to find out which alternative is appropriate to meet what kind of social requirement, what kind of economic requirements, and so on. Design an instrumentation system for managing available water and its utilization in a river basin, which is a very complex issue. Design a system for construction of large-scale poor and middle class housing in towns with populations less than 2 lakhs. What works in a city may not work in a small town. Improve the quality of power supply to a city or a district. Design a system for managing an elephant corridor without conflict between humans and elephants. These are some varied examples which you can say they are complex in nature. And coming to complex engineering activities, they are labeled by Washington Accord again as EA. EA are engineering activities essentially. Complex activities means that have some or all of the following characteristics. EA1 involve the use of diverse resources including people, data and information, natural and financial and physical resources, and appropriate technologies including analytical and or design software. Okay, you are using very diverse resources. Somebody will have to make decision. You cannot say I know only about financial operations. You cannot say that. So all of them will have to participate, and whoever is coordinating will have to understand the interrelationship between all of them. Another activity, require optimal resolution of interactions between wide-ranging and conflicting technical and non-technical and engineering issues. EA3 involve creative use of engineering principles, innovative solutions for a conscious purpose, and research-based knowledge. Have significant consequences in a range of contexts and characterized by difficulty of prediction and mitigation. What happens is you assume certain conditions and you design the total project, but what happens after a period, things around that do change. When they change, what you consider a solution may not be effective and sometimes even lead to different set of problems. So one has to look at what happens when the context gets completely changed. If you look at let us say like a project like Narmada project, you displace people, you give them compensation, all right, but that gets translated into altogether a completely different social and economic problem in a different way. Now, who solves that? But you have created a problem for yourself by solving another problem. EA5 can extend beyond previous experiences by applying principles based approaches. What it means is people would have accumulated certain experiences and you cannot make conclusions exclusively based on your experiences. We have done this is what we are experienced and so on, and many times it may extend beyond that. That means you have to think afresh. Okay, let us now come to the first PO1, which is labeled as engineering knowledge. Once again, we'll read that apply the knowledge of mathematics, science, engineering fundamentals, and an engineering specialization to the solution of complex engineering problems. And it must have from the knowledge and attitude profile WK1 to WK4. Okay, this is the way the PO1 is written by NBA. Now, personally, I would like to reword this statement because the focus is on what? There are two aspects. One is applying knowledge of mathematics, the other is solving of complex engineering problems. In my opinion, solving the complex engineering problems is the goal. And you are saying how do you solve? Not intuitively, not arbitrary manner, but through application of knowledge, mathematics and so on. So if I reverse the order, the same statement can be said, solve complex engineering problems applying the knowledge of mathematics, science, engineering, fundamentals and an engineering specialization. Okay, it's the same thing, but the focus is on solving complex engineering problems. Majority of engineering courses, I wouldn't say mainly address this, but they address at least part of this. Instructional assessment in many institutions falls far short of solving engineering problems, leave alone complex engineering problems. That is what you have to understand. As it is practiced now, first of all, I do not know other than some project, even there very rarely, any engineering program addresses complex engineering problems at all through its courses or projects. First that. And then on top of that, if you look at the total number of courses that you have, about 35 or 40, majority of them are basic sciences, humanities and then engineering sciences, but the number of engineering courses do not count more than 6 or 7. Any branch you take and keep marking which do constitute engineering courses, but majority of them are engineering science and basic science courses. That is the first thing. And engineering sciences courses do not address engineering problems. They address only underlying engineering science. But they can be redesigned to a certain extent that at least some engineering problems can be addressed through the engineering science courses, but that it requires a lot of effort on the part of the faculty to revamp the course, the content and the examples that you work on and so on. Normally we aim at what you call end of the chapter problems. End of the chapter problems, what do they do? In every chapter you introduce certain concepts, and then using those concepts you solve very limited, what you call well defined problems. Maybe you depend on the knowledge or the techniques that are offered in the previous chapters, but you are only confining just exactly, well, you are checking out at the end of the chapter whether you have understood what was presented in that. That is not solving engineering problems. That is solving engineering science problems. So to that extent, end of chapter problems will moderately address this PO. You cannot say it doesn't address this PO, it will address moderately. Basic science or engineering science courses, as they are offered in most of the institutions, do not address engineering problems directly, as I mentioned. However, these courses can be designed to address engineering problems to a certain extent. Now, what are the activities aiming at PO1? These activities should not only reinforce theoretical knowledge but also teach problem solving, critical thinking, and the application of interdisciplinary concepts, allowing students to address complex engineering challenges effectively. Okay, we are giving some activities in different branches of engineering that can address this PO1 adequately. Okay, design and build a robot that can perform a specific task, integrating principles of mechanics, electronics, and computer programming. So it is all multidisciplinary, it is fairly complex, there are a lot of conflicting requirements and so on. And you have access to limited resources and so on. Conduct experiments to understand heat transfer processes and apply them to optimize thermal systems like engines or HVAC systems. Implement algorithms to filter and transform signals, addressing noise reduction in communication systems. Design beams and columns for a given load using software simulations, applying principles of material science and physics. I will not read through all of them. One or two I will mention. Implement a real-time operating system on a microcontroller, which is a complex problem to a certain extent. Design and test flight simulation models utilizing aerodynamics, propulsion and control systems knowledge. So these are some examples of activities. If they are involved in your program, then you are addressing PO1. But through which course, what activity you are doing, that you have to be clear. You cannot attribute that you have addressed the PO1 in all other courses as well. You have to be specific. And here you may want to use some kind of scaffolding. Start with something simple and keep on building on top. After you resolve, you go to the next level, like solve end of the chapter problems. That cannot be the end itself. Okay, understand the context in which a given engineering problem was formulated. Understand the nature of complex engineering problems. Give examples of complex engineering problems. Give multiple solutions to a given complex engineering problems. The idea is, if you go through these phases and explain the complexity, like take a specific complex engineering problems and try to elaborate on that. What is the nature of that? And give multiple examples in your own discipline, and give multiple solutions to a given complex engineering problem. The teacher has to do considerable amount of homework, collect a lot of information, and make students participate, and so that they understand these issues. Okay. So through some scaffolding, if you go through this, you are preparing him to address complex problems. Now we come to PO2, problem analysis. This is a little misunderstood PO2 based on our, we have been interacting with a lot of colleges. They, without thinking the moment analysis is identified, they tick, yes, we are doing analysis, and they consider just by that word, I am addressing PO2. Okay, what is PO2? Identify, formulate research literature and analyze complex engineering problems, reaching substantiated conclusions using first principles of mathematics, natural sciences and engineering sciences. If you look at what are all the activities involved in that, in addressing this PO, problem identification, as stated in the as given in the statement itself. I am not adding anything new. Problem identification, formulation, researching literature, analyzing and reaching substantiated conclusions. There are 5 activities. At least you should be doing one or more of these activities when you say I am addressing PO2. First one is problem identification. Are you identifying problems? Somebody is giving you a problem like end of the chapter problem. So you are not identifying any problem. Neither you are formulating. Somebody has formulated and asked you to solve. Are you researching the literature related to that? And are you analyzing? Analyzing is a word, as we will see in the later units, is a kind of very loosely used word. Everybody uses the word analyze without specifically meaning something. Because we have been using, we don't feel uncomfortable using that word. We use very specific meaning for that, as given in the taxonomy that we will look at in the 3rd week of this course. And you have to reach substantiated conclusions. That is these are the 5 activities involved. When you are trying to say that I am addressing this, you should be able to justify to somebody one or more of the sub activities that you are actually addressing. So here PO2 involves, in another way, problem statement construction. We can vaguely say something like design an instrumentation system for let us say for a dam. Okay, leave river water basin and all that, just for a dam. But that is only your vague wish statement. But it has to be converted into a very comprehensive problem statement. What variables you are going to measure, why should you measure those variables, and so then you have to identify what is the range of these variables. All that will have to come first level problem statement, and then you convert into problem formulation and abstraction. Then information and data collection. You have to collect data related to that that whether your problem formulation and abstraction are appropriate. Then you model, then you validate the model, then you do experimental design, then you actually perform experimentation, and then you interpret the results that come from that. Then you implement, then you document, then you get feedback. Based on feedback, you improve. All these activities are involved, really speaking, in implementing PO2. Are you giving experience to as many things as possible in this? If you are giving a chance to student to understand or participate in these activities, then you are addressing PO2. If you are not, you cannot just based on one word analysis, you cannot tick that box. And people have been doing that. It is being unfair to the students, saying that I am doing what I am supposed to do without actually doing it. Further, substantiated conclusions should be arrived at using first principles of mathematics, natural sciences, and engineering sciences, and not based on opinion or intuition. So, any conclusion that you want to draw should be based on underlying what do you call either underlying either mathematics or natural sciences and engineering sciences. Majority of the programs do not have courses that address even a small subset of these activities of PO2, not even a small subset. So, if you look at the courses, their curriculum and the what do you call examination papers, you can come to the conclusion that PO2 is not addressed, whether they tick that box or not. These activities can only be included in mini and major projects, provided they are properly orchestrated. PO2 as of now can be to a certain extent addressed through mini and major projects. But even there, you have to properly orchestrate. Proper orchestration means you define what the rubrics by which you are evaluating the performance with respect to those projects, and are you holding the hand about the way they should be conducting these projects. The PO can also be addressed through group assignments. In some courses, this requires considerable planning on behalf of the instructor and developing appropriate rubrics for evaluation of performance of each member of the group. It can be done. We will look at these kind of group exercises in the following course actually on instruction. Some examples of PO2 activities, again from different disciplines. I will read out two of them and the rest of them you can read further. We will make this slide information available to you. Specify the hardware, software, products and processes that can produce the solution to the formulated engineering problems. Investigate the causes of mechanical failures in components using principles of mechanics and materials science to draw conclusions and propose solutions. The way the activities are presented to you, they are still very generic, they are not specific. Okay. So, but within this broad framework, you can design several problems, like for example, causes of mechanical failures of components. Which component? There are any number of components. So, one can convert into a more concrete problem like that. Model and simulate dynamic systems, example vehicle suspension, requiring literature research to understand underlying principles and current methodologies. Formulate and solve problems related to load flow in electrical grids using mathematical modeling and research to optimize system performance. So, we have some more examples related to infrastructure projects or structural failures, and for example, identify and analyze security threats applying algorithmic principles and researching current solutions to propose robust defenses, especially cyber attacks. So, as you can see, PO2 is not something simple. It is not just a matter of ticking a box. You have to do elaborate planning in some identified courses, and this exercise should be done by all the faculty of a department sitting together and planning, not planning each course according to convenience of a small group of faculty. It is a departmental responsibility. If you ask the question, where am I addressing PO2? The department should have a very clear strategy and an answer. And in the next unit, the W2U3, we will look at the activities that need to be done to attain PO3, PO4 and PO5. And thank you for your attention.